There are different ways of representing aqueous reactions. The molecular equation is what we're probably most familiar with. This shows complete neutral formulas for all of the compounds involved. So this is an example. The equation that we just wrote in the previous problem is a molecular equation. It's showing potassium hydroxide as a compound. It's showing magnesium nitrate as a compound, AQ being dissolved in water. But what actually occurs when magnesium nitrate is dissolved in water is that the ions are separated from each other. So we can write a complete ionic equation which shows all the ions as they actually are. So the potassium and the hydroxide, they may have come to the reaction together, they came to the party together, but now they're separating and they're mingling with everybody else. Magnesium and nitrate are mingling, and after everybody meets, potassium and nitrate still mingling about. Magnesium and hydroxide, a solid, these guys had a chemical reaction, right? They are together. So the complete ionic reaction or equation shows everything as it actually is, separate ions or together. And then the net ionic equation, this is like your net paycheck, where they take out all that stuff that you're like, but there goes all my money, right? Just don't even look at your gross paycheck part. Just go to the net, and then you'll make it feel better. Just don't think about all the stuff they're taking out. The net ionic equation is kind of the bottom line. This shows only the things that actually change. So in this equation up here, potassium was soluble to start with, and it's still soluble, just hanging out by itself. Did anything really happen to the potassium? Did it get involved in a relationship? No, it's unchanged. We call those spectator ions. So we're not going to include those in our net ionic equation. Let's talk about the complete ionic equations first. So anything that's an aqueous strong electrolyte is going to be written as separate ions. Separate ions have charges, those need to be included. So these would be soluble salts. Salt is just another word for an ionic compound. Strong acids and strong bases. Anything that's insoluble is a weak electrolyte or a non-electrolyte is going to be written as a molecule. So these would include solids, liquids, and gases. There are a few things that are aqueous that are not written as ions, but those are the exception rather than the rule. Weak acid is really the only one you need to be aware of. So here is our molecular equation, lead-2 nitrate reacting with potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. Anything that has AQ as its state symbol is probably going to be written as separate ions. The exception would be weak acids. So this is aqueous, so I'm going to write the two ions with their charges separately. PbNO3 there's a lead ion, and this 2 tells me there are 2 nitrate ions. It's not NO3 as a single ion. Excuse me, there are 2 of them, right? So how does that work in the relationship party analogy? I don't know. Maybe these 2 are twins and they both came with lead. I don't know. You could take that any way you want to. Then over here, potassium and chloride, aqueous, so we're going to write potassium ion and chloride ion separately. There were 2 of these units, and so we have 2 potassiums and 2 chlorides. This is a solid. Solid, just copy it down. Liquid, gas, just copy it down. Don't do anything to it. And then here's another aqueous one, soluble ionic compound. We need to write this as separate ions. Any questions? This is called a complete ionic equation. Most of the time it's actually just a step towards the net ionic equation. So we've got all of the ions shown, and some of these didn't get changed. They weren't involved in a chemical reaction. Nitrate, we had 2 nitrate ions before, and we still have 2 nitrate ions. We had 2 potassium ions, and we still have 2 potassium ions. They didn't get involved in a relationship. There was no chemical reaction with them. They're spectators. They're watching the other things going on. So lead 2 chloride. They're like, ooh, look at those guys, right? They're really having fun with each other, whatever, I don't know. So in the net ionic equation, we get rid of the spectators. So this is a spectator, and this is a spectator.
So if you're on both sides of the
Yes. Anything that is the same on both sides of the arrow is a spectator. Because would this reaction between lead and chloride happen if lead came with somebody else like acetate? Yeah. Nitrate has nothing to do with this chemical reaction. It just happened to be there. So we cross those out, and then we copy down what's left. And this is called the net ionic equation. So these are just the things that are involved in the chemical reaction. Any questions? The nitrate ion and the potassium ion, I guess you could say there's a rule at this party. You have to bring a date. You can't show up by yourself. You have to bring a date. And so lead brought nitrate. Would it matter if lead brought somebody else? No, he just had to bring somebody, right? And chloride had to bring somebody. Chloride brought potassium. Maybe she could have brought ammonium or lithium or, sodium. It wouldn't matter. When lead and chloride saw each other, they would form a solid. They're going to be attracted to each other and get into this chemical relationship, right? Regardless of who else is at the party. But you can't just have lead ions, because things really want to be neutrally charged. And so you can't have a beaker just of lead ions. There has to be, we call them a counter ion. If this is a positive ion, there has to be negative ions present as well. But they may not get involved in the relationship. So here's a practice. Consider the following reaction occurring in aqueous solution. Write the complete ionic and net ionic equations for this reaction. So we're given the balanced molecular equation. That was nice. So what we're going to do is we're going to look at these and look at the state symbols. And if it's AQ, we're probably going to separate it into ions. Have we talked about strong acids? I can't remember. Well, we've talked about what acids are. Hang on just a minute. So we have talked about strong acids. We did that when we were back here talking about strong and weak acids with strong and weak electrolytes. We didn't identify which ones were strong and weak, though. So HI, aqueous, this is an acid. So we do need to ask ourselves, is this a strong or a weak acid? I don't know why your book does this, but it does. It hasn't told you which are the strong acids yet, so I'm going to tell you right now. HCl, HBr, HI, HClO4, HNO3, and H2SO4. There are 6 of them that are significant. Those are strong. Any other acids that you see are weak acids. Weak acids only ionize a little bit, and so we don't write them as ions. But here we have HI. HI is on the list. A strong acid ionizes completely. It separates into ions. And so we're going to separate this into ions. Here we have a soluble ionic compound. It happens to be a base. we're going to separate that into ions. L, liquid. Am I going to separate that into ions? No. Just going to copy it down as is. Here I have another aqueous compound. I'm going to separate that. So 2HI. Well, the ions there are hydrogen ion and iodide ion. And it'll end up balanced if we pay attention to what we're doing. Here, there are two of these units. Each unit has one H and one I. So when we separate that, I'm going to end up with 2 hydrogen ions and 2 iodide ions. Next is the barium hydroxide. The ions present there are barium 2+ and hydroxide. From this formula, how do I know that the ion here is hydroxide, OH-? Because I should recognize these ions, right? In Chem 1A, ionic compounds always contain 2 kinds of ions. One cation, one anion. That's not true outside of Chem 1A, but it is in Chem 1A. So I'm not going to split this into barium and oxygen and hydrogen. The first element is a metal, that's the cation. Everything else is the other ion. If it's more than one element, it's a polyatomic ion. If you don't recognize it, go look at the list of polyatomic ions and find it. So OH- is the other ion. From this formula, I can see that there's 1 barium and 2 hydroxides. So I'm going to put a 2 in front of hydroxide. It's a little bit like a bicycle where you have a frame and 2 wheels. And if you take that apart, how many wheels do you have? You have 2 wheels, right? And 1 frame. Over here, this one is a liquid, and so we said we just need to copy that down. 2H2O liquid. And then we have barium iodide, another soluble ionic compound. So we write the ion with its charge, and the other ion with its charge. And we look at the formula. We have 1 unit. In 1 unit, I have 1 barium ion and 2 iodide ions. That's the complete ionic equation. Any questions? You can probably see it if you're a little weak on the whole nomenclature business and writing ions and predicting formulas. This is going to be harder, right? Because we have to be able to do that. So the net ionic equation, I'm going to look at my complete ionic equation and identify who is the same as a reactant and a product. So do I have anybody like that in this equation? Iodide. I have 2 iodides here, and I have 2 iodides over there. She did not change. Anybody else? Barium. Got a barium 2+ ion here, and a barium 2+ ion there. What happens after the party? Well, H2O is a thing now, and these guys just leave with each other, but they're not together, right? So I cross off my spectators, and then I'm going to copy down what's left. 2H+ aqueous plus 2 hydroxide ions aqueous, forming 2 water molecules liquid. Now what's a little funny about that equation? Everything's 2s. A balanced chemical equation really should have the lowest coefficients because there should be one best answer. Because I could write this 200 H plus 200 OH- makes 200 H2Os. But then I literally have an infinite number of equations I could write. And we like to have one correct answer. So we're going to go with the lowest ratio. So ideally, you would see that all those coefficients can be divided by 2. And so it's H plus OH minus, making H2O. Any questions? If you can picture these ions as those little, they're like Lego things, except they're round, right? If you can picture them and picture them coming apart and switching partners and stuff, then writing equations like this is actually pretty easy. If you're stuck in looking at all of the letters and not having a representation of them in your head, then this becomes much more difficult. So if you're having trouble with this, come talk to me and we'll get the model kit out and we'll play with toys until you say, oh, I see how that works now. And then it'll be so much easier.